In this video, we'll begin our discussion of causal graphs, a very powerful tool for thinking through exchangeability and for modeling data in causal settings. A causal graph is a diagram that looks like this. Variables that are relevant to a causal investigation are connected by arrows. They'll be immensely valuable to us because, as we'll see, they're actually depictions of statistical models. For this reason, they'll help us harness our subject matter knowledge to design for exchangeability across a wide range of study designs, and they'll help us analyze data appropriately to answer causal questions. In this video, we'll introduce key terminology surrounding graphs and causal graphs, and in the following videos, we'll develop key statistical properties of causal graphs. Formally, graphs are mathematical objects that are collections of nodes or vertices, indicated by the circles, and edges, linking the nodes, indicated by the arrows. In the case of these arrows, the edges are called directed edges because the connections between nodes have a direction. A graph whose edges are all directed is called a directed graph. If the edges connecting the nodes did not have directions, the edges would be called undirected edges. A graph whose edges are all undirected is called an undirected graph. In causal inference, we'll primarily deal with directed graphs. Two nodes are adjacent if they're connected by an edge. So in this example, x and y and z are adjacent, but x and z are not adjacent. A graph is called complete if every pair of nodes is connected by an edge. So in the left graph, all three pairs of nodes are connected, but in the right graph, x and y are not connected, so that is an incomplete graph. A path between two nodes, x and y, is a sequence of nodes that starts with x and ends with y, such that there's an edge between consecutive nodes on the path. So in this graph, xmy and xzy are the only two paths from x to y. When people write paths in text form, they tend to write them in a single line of text like we've done here, with the arrows pointing either left or right as indicated by the graph. So xmy is called a directed path because it follows the direction of the edges. Each node, other than the start and end node, have one edge going in and one edge going out. xzy is called an undirected path because it ignores edge directions. In an undirected path, any number of the middle nodes can have edges both pointing in or both pointing out. A cycle is a directed path that starts and ends with the same node. A graph with no cycles, like the top graph, is called acyclic. We'll end our tour of graph terminology with other descriptors of the relationships between nodes. X is the parent of y because the edge between them points from x to y. Y is also the parent of z. So correspondingly, y is the child of x and z is the child of y. In a directed path, ancestors of a given node are any nodes that are upstream of that node, and descendants of that node are any nodes downstream of that node. So in this graph, x is an ancestor to y and z, and y is an ancestor to z. Y is a descendant of x, and z is a descendant of both x and y. So now that we've defined important graph terminology, we can discuss what makes a graph a causal graph. Causal graphs are also called causal diagrams or graphical causal models. In particular, causal graphs are directed acyclic graphs that have a few key properties. Nodes represent variables. A directed edge from x to y means that x is a cause of y. Directed, as opposed to undirected edges, model the flow of time, and that causes should precede their effects. The lack of cycles indicates that time should not flow backwards. The presence of a cycle would indicate a cause happening both before and after its effects. And for any pair of variables in the graph, all common causes of those variables in the pair are also in the graph. So for a pair of variables x and y, all variables that cause both x and y are shown in the graph. Let's discuss the acyclic property in a little bit more detail. It would seem that a lack of cycles in graphical causal models would be a limitation. Feedback loops are a common occurrence in all sorts of situations. So for example, joy and exercise might exist in a positive feedback loop. Joy leads to increased exercise, which heightens joy. We can actually represent this feedback loop by creating separate variables for both joy and exercise that correspond to earlier and later points in time. We'll discuss the idea of time varying quantities in more detail later, but for now, know that it is possible for causal graphs to capture feedback loops, which are common in many situations. So, the key idea that makes causal graphs so useful is that they're actually statistical models. The variables represented by nodes can actually be regarded as random variables, and the edges connecting them indicate that some variables are quantitative functions of others. In particular, edges pointing into a node indicate that the probability distribution of the child variable is conditional on, the values of the parent variables. We'll discuss causal graphs as statistical models in the next video. This will set us up to understand how lack of exchangeability arises, and thus give us strategies for achieving conditional exchangeability so that we can estimate causal effects.